Okay, well, let me try to explain where we're going with the rest of this chapter. We've talked about reduced echelon form. We've talked about how row equivalence divides the set of all matrices up into equivalence classes. And what we want to show with the rest of this chapter is that in each class, there's one unique matrix in row echelon form. In other words, each class here, each one of these has exactly one matrix that is of row echelon form. And that's kind of the characteristic matrix for that class. And in fact, any matrix in a particular class will correspond to a system of linear equations. And the solution of that system will be given by that unique reduced echelon form matrix. Okay, so as long as I know matrix A is reducible to a particular matrix of reduced row echelon form, I know the solution for the system of equations represented by A. Right. So let's see how that works in subsequent slides. We're going to prove this by proving various facts about linear combinations. Right? So think about how Gauss's method works. Whenever we do one of these row operations, we're actually taking linear combinations of the rows of the matrix. So for instance, go from here, I'm taking this linear combination of row 1 and row 2. Okay. So we can represent this just by considering the rows of the matrix. So alpha 1 and alpha 2 represent the two rows of this matrix. Once I apply this row operation here, the new first row, which I call delta 1, is equal to the old first row, which is alpha 1. The new second row, which I call delta 2, is equal to this linear combination of the old first and second row. If I continue this process and I apply this row operation to this sequence of rows, this row operation does not change the first row, so the first row is the same, and in fact it's the same as my original first row. The second row gets multiplied by minus 1/2, which means I multiply this second row here by minus 1/2, giving me this. Now if I apply this row operation here to this matrix, in this case the second row doesn't change, the first row changes. The upshot is that the final rows that I obtain are linear combinations of the initial rows that I started with. And that's what we're going to prove. This will be a very useful fact in showing that the reduced row echelon form is unique. Okay, so Gauss's method systematically develops linear combinations of rows. Okay. A linear combination of linear combinations is a linear combination. Right, so what are we talking about here? Let's go back to this example here. What we've done to obtain these two rows is take linear combinations of these rows. Then here, we take linear combinations of the rows here. So we can call the result here a linear combination of linear combinations. That's what we're doing when we do row operations. Every time we do a row operation, we take a linear combination. Then the next row operations take linear combinations of the result. Okay, so let's prove this. Okay. So let's do this simply by construction. All right, here is a linear combination of the x's. Okay, these x's could be considered as row vectors. Actually, this is true in general for any type of vectors, but in our application, we're thinking of the x's as row vectors. Okay. So we're taking this linear combination, and if we take a linear combination of linear combinations, all right, I should say more clearly that here we have m different linear combinations. That's why we have two indices on the C. C11x1 through C1nxn, that's my first linear combination. My second linear combination will be C21x1 plus ... plus C2nxn. That's my second linear combination. Altogether, I have m linear combinations. And I'm going to take a linear combination of these m linear combinations. The coefficients of this linear combination will be the d's. Okay? Since I have m linear combinations, I need m coefficients d. And this is the expression of the linear combination of linear combinations. Now I just rearrange using ordinary algebra. Actually, I'm using the distributive property to pull the d's into these expressions. And then I group like terms. If I group all the coefficients of x1, I get this result. I'll have coefficients of x2, I can group those, etc., etc. I can group all the coefficients of xn, and I get this result. And notice that this expression is a linear combination of x1 through xn. It's a sum of scalar multiples of the x's. So that completes the proof that this linear combination of linear combinations is itself a linear combination. All right, a corollary. Corollary is an immediate result of this previous result. So the corollary, when one matrix reduces to another, each row of the second is a linear combination of the rows of the first. And the proof of this, for any two interreducible matrices A and B, there's some minimum number of row operations that will take one to the other. So we proceed by induction on that number. In other words, you can imagine going from A to B. There may be a sequence of row operations. Perhaps there may be a sequence of 5 row operations that takes A to B. All right? So there may be another way to reduce A to B that takes only 3 row operations. There must be a way that has a minimum number of operations. It can't take less than 0 operations. And if A is not equal to B, it can't take 0 operations either. Right? So we're going to identify the minimum number of row operations that takes A to B, and we can proceed by induction on that number. In other words, first we prove it for matrices A and B so that A takes only 1 operation to get to B. Then we prove for matrices that A to B that takes only 2 operations, and so on. Okay, so in this particular proof, our base step, the minimum possible number of row operations is 0 row operations. Okay. In the case where A can be taken to B by 0 row operations, then of course A is equal to B. Each row of B is equal to each row of A. Since the rows are unchanged, certainly that means that the rows of B's are trivial linear combinations of the rows of A. All right, because for instance, if I say the ith row of B is equal to the ith row of A, I can write it in this way, which indicates that the ith row of B is a linear combination of the rows of A. All right, so what have we shown? We've shown that if A can go to B in 0 row operations, then the statement is true. The rows of B are linear combinations of the rows of A. All right, so now we assume that we have shown this result for K or fewer operations. Okay. Now, consider a matrix B such that reducing A to B requires K plus 1 operations. In that reduction, there is a next to last matrix G, so that A, on the way of reducing to B, passes through G. However, A reduces to G by only K operations. Now, by the inductive hypothesis, we know that our result is true when we can obtain the second matrix from the first by k or fewer operations. In other words, G, the rows of G are linear combinations of the rows of A. Okay? So that's what we have here. Now, we want to show that the rows of B are linear combinations of the rows of G. Okay, then we can use the linear combination lemma, because we know that the rows of G are linear combinations of the rows of A. And if we can verify the rows of B are linear combinations of the rows of G, that means that the rows of B are linear combinations of the rows of A. Okay. All right, so here we're repeating the stuff we've shown about row operations. In fact, B is obtained from G by one of the three row operations. And each of the three row operations represents a linear combination of the rows of G. For example, if the operation taking G to be is multiplication of row by a scalar, then the ith row of B is equal to C times the ith row of A, and the other rows are unchanged. So that means that all the rows of B are linear combinations of all of the rows of G. Okay? Or if the row operation is adding a multiple of one row to another, then in the same way, that new row of B is simply a linear combination of the rows of G, and the other rows are unchanged. So in any case, the rows of B are linear combinations of the rows of G. The rows of G are linear combinations of the rows of A. By the linear combination lemma, we have the rows of B are linear combinations of the rows of A. Okay? All right, let's continue. Another helping result that will help us get our final result is that in an echelon form matrix, no non-zero row is a linear combination of the other non-zero rows. Right, if you think about the form of an echelon matrix, this result is not too surprising. Let's take an echelon form matrix and consider the stair-step form. Right, we know that in an echelon form matrix, it looks something like this. Okay, and we have zeros down here. What I'm representing here, this is the leading entry of this row. This is the leading entry of this row, leading entry of this row, leading entry of this row. All right, now suppose I took a linear combination, say, of this row, and this row. Well, notice that this row and this row don't have any entries in this column. This has a 0 here, and this has a 0 here. So if I take a linear combination of these three, then it's necessary that the entry here in this column will have a non-zero entry. And that's actually the idea that we're going to use. If you take a linear combination of rows, then the lowest row will have a leading column, and the entry in that leading column will be non-zero. Okay, so let's go on and see how that works. Okay. All right, so let R be an echelon form matrix. So consider the picture that I just drew, and consider its non-zero rows. First observe, if we have a row written as a combination of the others, this one row, row I, is a linear combination of these, then we can rewrite the equation as follows. We can put the row I over here together with the others. So here we have a linear combination of all the rows is equal to 0. Okay. And all these coefficients can't all be 0, otherwise you can't say that this is a non-trivial linear combination of these rows. Okay. And we can choose, well, for instance, in this case, if we take the row I to the other side, then we're going to have a minus row I term. And that means that the coefficient of row I in this expression is -1. All right, now, the converse holds also. Given if we have such an equation, and one of these CI's is not 0, then we could express this ith row by solving for CI row I, and then dividing by minus CI. Okay. Therefore, as long as we can prove that all the coefficients here must be 0 whenever we take a linear combination of rows of an echelon form matrix, as long as we can prove that the only way to get 0 as a combination is with all the CI 0, then we've proven our result. Okay. And we're going to do induction on the row number I. So in other words, we're going to prove first of all that the first row is not a linear combination of the other rows. And then we're going to go prove subsequent rows by induction on that result. Okay. And the base case is the first row. If there is no non-zero row, then R is the zero matrix, so the lemma holds. We don't need to worry about that. So let Li be the column number of the leading entry in row I. Now here we're considering I equal 1, so let me just draw that picture. We have our matrix here. And here we have zeros. We can have a row echelon form and have zeros here. We have zeros going up to here. And then this is column Li here. Okay, that's called, well, because I equals 1, that's column L1. So here I have an entry that's non-zero.